Continuing with the discussion on equilibrium criteria, in the last session we've seen that when the machine is connected to the motor, that is the synchronous generator is connected to the motor through a line, then the power delivered or the power output of a generator is nothing but the input to the synchronous motor. In that case, what is the power transferred? In the event of any change of the output of the synchronous motor, then what happens to the load angle? What happens to the speed? Then how exactly there is attaining the new balance condition that we were discussed in the last class. Just we will review once again. That is a power delivered by the generator, that is the output of the generator, which is given by Eg by Em by Xt into sin delta, where Xt is it is a total reactance from generator to the motor, that is it is a comprises of Xg, XL, that is transmission line reactance, and the motor reactance. This P is nothing but the input of the synchronous motor. Then we have drawn the power angle characteristics for the output of the generator, which is the input to the synchronous motor. That is P is given by P max sine delta. That is P max is nothing but it is Eg Em divided by Xt is the P max. Then previously when there is no change in the output, then initially the machine is operating at point A, where the electrical input to the motor is equal to the mechanical output of the motor. Then that is operating at the point A with the mechanical output and the electrical output are equal, and it is operating at an angle of delta. Now, if you are suddenly increasing the mechanical output of the machine, then the operating point A has to shift to the operating point B, because the mechanical output is greater than the electrical input. Therefore, in that case, to adjust to the new value of B, the angle delta has to be changed here. Now, electrical input is less, mechanical output is more. In that case, there is a deceleration. Because of that, the speed is decreasing. However, angle delta goes on increase along from A to B. But when it is reaching B, both the mechanical output and the electrical input has becomes equal. However, because of the inertia of the machine, the angle delta goes on increasing beyond B, that is to the point C. What happens when if it is moving from A to B? I told you that there is a deceleration because of the speed goes on decreasing. At point B, you are getting the speed less than the synchronous speed, but delta is still it is tendency to increase, but the speed is less than the synchronous speed. Therefore, delta goes on increasing. Our speed is also goes on increasing because beyond B, the electrical input is more than mechanical output. Therefore, the speed is gradually increasing from B to C. When it is reaching point C, the speed is become synchronous speed. At that point, the angle delta ceases. That is, it remains constant here. Now, when if you are considering point C, considering the point C, in that case, the electrical input is greater than the mechanical output. Therefore, there is an acceleration. Therefore, what happens? Because of the acceleration, the angle delta has to be decreased. The angle delta has to be decreased. Therefore, then operating point once again shifting from C towards B. Now, angle delta goes on decreasing. However, when it is moving from C to B, electrical input is greater. Therefore, still the speed goes on increasing. At point C, you have got a 1500 rpm. When it is moving from C to B, the speed go beyond the synchronous speed. Then when it is reaching the point B, we are getting a maximum speed. We are getting a maximum speed which is greater than the synchronous speed. Once again at point B, both mechanical output and electrical inputs are equal. But however, because of the inertia, delta goes on decreasing. decreasing because of the inertia. Then from when it is moving from B to A, mechanical output is greater than electrical input, therefore there is a deceleration. Means at point B you are getting a maximum speed, from B to A the speed is goes on decreasing. When it is reaching to the A, the speed is once again it is synchronous speed. Here once again the cycle repeats. Suppose if you have got a damping torque, then this oscillation that is moving from A to C, C to A to C is goes on decreasing in magnitude. Ultimately finally it is reaching at steady point of B. The same thing is explained yesterday, that is the system is stable when A1 is equal to A2. That is explained with the help of this table. Then when if you are moving from A to B, B to C, C to B, B to A, once again the cycle is repeating because of the damping torque in the machine. Then it is settled down finally at point the B, that what was seen in the last class. Now in this session we will look into the how much you can increase this particular the output machine, so that the machine should not lose its synchronism. How it is, what is the transient stability limit, what is the maximum limit, that we are interested. That the maximum swing of the torque angle delta m can be found by the equal area criteria. That is, if you are go on increasing your ps, so that a1 must be is equal to a2. When if we are getting A1 and A2 are equal, till that point the system is stable. Once if your PS is increasing in a such a way that in that case A1 is not equal to A2, then the system is losing its synchronism. That is how it is explained here. The maximum swing of the torque angle delta m can be found by the equal area criteria by equating the shaded area of A1 and A2. Therefore, if we look into A1, area under this curve, that is a decelerating curve, that is it is from the limit delta naught to delta s, it is a Ps minus P. Here in the deceleration, because the mechanical power output is greater than the electrical input into d delta, then the variation is from delta naught to delta s. That is quite evident here in this figure. Means here from delta naught to delta s, here it is Ps is greater than P, therefore it is Ps minus P. When if we are moving from B to C, that is area A2, when if we are looking for the area A2, in that case electrical input is greater than the mechanical output, it is P minus Ps, therefore there is a change in the angle is from delta S to delta M. Therefore you have to take area under this curve, that is the accelerating curve, area under this curve, that is decelerating curve, must be equal. The same thing is given here. The area A2 is given by A2 is equal to, it is between ds to dm. Here you can observe, here it is P minus Ps into d delta. Then the system is stable when A1 and A2 are equal. Then when A1 is equal to A2, the condition for d delta by dt is equal to 0. When both the areas are equal and the change of the angle delta is ceases, so that d delta by dt is becomes 0. Therefore, the system is stable. Now, we are interested in, let us find out the maximum value of Ps such that the system is critically stable. That is, up to that point the system is stable. If we are going beyond that, then it is losing its synchronism. That point what we are calling is, it is a critically stable. Critically stable means that is a point at which the system is stable. If we are going beyond that critically stable condition, then it is losing its synchronism. What is that critically stable condition point that we will see now? Any attempt to increase PE beyond this value, system becomes unstable. If you are going beyond this critical point, then the system is losing its synchronism. Okay, just I am putting here a figure here. What is the electrical input to the machine? Previously it is operating at point P at A. At this point, that is the input is PS, PE and the output is PS. Both PE and PS are equal at point A, therefore system is stable. Now I am increasing the output of the machine, the output of the machine from the initial condition to here. I am increasing here. I am increasing the PS at this point. Then the operating point will shift here from A to B here. Then it is moving to this, and it is after all that is because of the damping torque, that is area A1 and A2 are equal, therefore the system is stable. Okay. Further, if you are increasing the mechanical output, instead of here, I am increasing from this value to this here. Once again, what happens here? If I am increasing my output of the machine to this value, this one, that is, I am increasing the value to this, therefore operating point is shifting here, therefore this is your decelerating area. Then it is reaching maximum swing is here, it is point C, it is point B, here it is accelerating area. Once again the system is stable. Now further I am increasing the output of the machine to this value. In this case, my decelerating area is A1 here. This is operating point B, but the maximum swing is occurring at point C. This goes up to this point C. Here your accelerating area, it is your A2. Now here just A1 is equal to 8. Suppose if you are increasing the output beyond this line, suppose I am increasing to this value as a PS now. In that case, your decelerating area is this, whereas your accelerating area is this 8. Here the A1 is not equal to A2, then the system is unstable. That is, it is a critical point where at this particular point both A1 and A2 are equal. If you are going beyond this value, then the system is the unstable. That is what he is telling, that it is a critical, the point where the electrical input must be is equal to maximum mechanical power output on the machine. Therefore, what he is telling, that any attempt to increase PE beyond this value, the system is become unstable. Referring to figure, that is, I am drawing here, this is the maximum, the PE what I am increasing. Here it is operating point B, and the maximum swing is, that is the decelerating area A1 here, then this is your accelerating area A2, just A1 and A2 are equal. If you are going beyond this value, then the A1 is not equal to A2, then the system is unstable. Therefore, the point B is called as critical point, that is corresponding to that angle of what you are calling as critical clearing angle, that is what you are calling as DC, or critical torque angle, what you are calling as critical torque angle. That is, for the maximum output you are increasing in a such a way that A1 just equal to A2. Beyond that, the A1 is not equal to A2, then the system is losing its synchronicity. This is how you have to explain the point of the critical point or a critical torque angle point, that is delta C.